So welcome back once again. Last video we discussed about the series combination of cells, and today the next one is the parallel combination of cells. So in this section we see what is the effective E.M.F of the combination, and then what is the effective internal resistance of the cell combination, not the external circuit, cell combination. And then we shall drive a kind of case where we go to the section what is the maximum value of current can be obtained, or under what condition maximum value of current is obtained if the cells are connected in parallel. Okay, so let's do it and get started. Parallel combination of cells. As in the last video, what we did is the cells were primary cells. So this is say one cell. For sake of convenience, we can take large number of cells, but for this practical purpose, we are taking only two cells. So this cell is, suppose, having E.M.F E1, and its internal resistance is given by R1. So this is one more cell, and they are connected in parallel between the 2 points A and B. And this one having E.M.F of E2 and internal resistance R2. Okay, this is simply the two cells have been connected in what? Parallel. Now we connect one external resistance, capital R, by this cell combination. So this cell has, or this cell will send current I1, this to I2, and when they combine at this point A, we get a total current called I. So this cell as was giving current I2, so it must take in the same current, that is again I2, and that is I1. If this is I, so the same current should flow through this resistance, capital R, and again at point B, what happens? The currents, that is I1, I2, gets again divided and go to the individual cells. So here point A, the two currents are getting combined, and at point B they are getting diverted or divided, right? So we have a relation between the terminal potential of cell E.M.F and internal resistance. Now see, importantly, what is the terminal potential of this cell E1 when connected alone? We don't have E2, suppose. So if this one is only connected and it's having a current I1, internal resistance R1, so the relation for cell I1, it becomes, for cell E1, the terminal potential between A and B. A and B is what? V A B is equals to E.M.F of the cell E1 minus I1 and R1. Okay, and this potential between A and B using cell first one, we can say this is equals to, or this is equals to V. So we shall take the value of I. So what is I? Is equals to E1 minus V over R1. This is the current drawn or given out by the cell E1. Mind it, this relation will be continuing as this is. Now if now cell E1 is not there, then what will be the equation for cell 2? Again we get, for the cell E2, the terminal potential again is given by V, and which is equals to E.M.F 2 minus I2 R2, and this is giving I2 is equals to E.M.F minus its potential over R2. Okay, so this has been established, the current given by the two cells. Okay, clear? Now at point A, what's happening? The two currents are getting added. So the net current, the total current at A, that is I equals to I1 plus I2. Okay, so put this value simply, E1 minus V over R1 plus E2 minus V over R2, and this is giving E1 upon R1 plus E2 upon R2 minus V over R1 plus V over R2. You need only to understand and do the simplification using simple mathematics. No need to use higher mathematics or higher sort of calculation. So this is again I is equals to, now V is common in the two terms, so we can take it out and it becomes R1 plus E2 over R2 minus V 1 upon R1 plus 1 upon R2. This again becomes E2 or E1 R2 plus E2 R1 over R1 R2 minus V R1 plus R2 and R1 R2. So this is the value of current. Now what we have to do is to find the equivalent EMF of this cell combination and equivalent terminal potential and equivalent internal resistance of the cell. Now we shall convert this equation in terms of this, that is V equals to EMF minus I product of R. So we should take V from here to the left side and let's do the calculation first. Okay, so this is what we got after solving or mixing the two currents I1 I2, and this is the effective current. So now we shall divide, or let's do one step ahead, that is E1 R2 plus E2 R1 over R1 R2 minus V R1 plus R2 and R1 R2. We want what? Terminal potential of this cell combination, that is V. So we shall divide the whole equation. Okay, whole means this complete equation by the term inside this square bracket. For that, what we get? And we shall replace V to the left hand side. So we get V equals to that is E1 R2 plus E2 R1 over R1 plus R2, right, minus I R1 R2 upon R1 plus R2. So this is becoming the first equation A, right? Now we shall compare this equation using what? The terminal potential is equal to EMF minus I into R. We have a single cell, but we have a combination of cells. So this is standing for what? The equivalent EMF. So we shall compare this equation A with this sort of equation. And what we get? If the language is like this, if equivalent is the equivalent EMF of the cell combination and R equivalent is the what? Equivalent internal resistance of the combination. So what we have to do is to convert this equation in terms of this, and finally we get, so now from equation A we get V equals to E equivalent minus I R equivalent. They simply give you what? That is equivalent EMF is equals to E1 R2 plus E2 R1 over R1 plus R2. This is my equivalent EMF of this two cell combination, right? And the equivalent internal resistance is given by product of the two internal resistance over the sum of theirs. This is what we have to find. The equivalent EMF of the cell combination, two cell combination, that is equivalent resistance of the cell combination. Okay. Now what if this term is divided by this? It's in the kind of expression that is E equivalent over R equivalent is equals to E1 over R1 plus E2 over R2. Mind this is for two cells. Now if we have n cells, then this equation becomes E equivalent over R equivalent is equals to E1 over R1, E3 over R3, and up to n terms. Okay, that is done. And if I revert this or simply take what you call reciprocal of this, then we get what? 1 over R equivalent is equals to 1 over R1 plus 1 over R2 for two cells. This is only for two cells. What if we have n number of cells? Then this shorter terms continues to n turns, and we get 1 over R equivalent is equals to this Rn. So this is the resultant equivalent resistance for the n cells in combination, that is parallel combination, and this is for two cells. I think this calculations have been so far simple, and you must be getting each and every step. Okay, now we shall go to the idea, what if the cells are identical? Means EMF of each and every cell is same, and internal resistance of these cells are equal to each other.